All right, so you have a Snickers bar. So what are some ingredients of a Snickers bar? So the first thing that you're going to touch whenever you touch that Snickers is what? Chocolate, right? We have this outside piece that is chocolate. All right. What else do we have?
Milk, egg, and soy.
Huh?
That's milk and egg and soy.
It does have milk, egg, and soy. The milk is actually in the chocolate. Oh, I have a brown marker. Did not know that. A little late now. All right. So, but what's next? What else do we have? We've got peanuts. We have nougat, which is a fancy way of saying some protein bonded sugar. All right. And then what else do we have? The good stuff. What's in the middle? Caramel. Wow, that's actually a really good color for the caramel. All right. So these are the ingredients for our Snickers. Chocolate on the outside. We have some peanuts. We have caramel. And then we have nougat. Now, each of these, I didn't leave myself enough space. Oh, well. Chocolate. What is chocolate made out of? Milk and cocoa. It is made up of milk, cocoa, and sugar. So it contains protein, fat, and sugar. Peanuts. Peanuts are composed of fat and protein, primarily. There's a tiny bits of carbohydrates. Caramel. Caramel made out of. Anyone know how to make caramel? Huh? Sugar. Full stop. It's actually technically sugar and cream if it's a cream caramel. I actually don't know if this is a cream caramel or not. I think this is just straight up caramel, which is just sugar and water. Okay? Or really not even water, just sugar. That's why it's awesome. And then we have nougat, which is made up of sugar and protein. You should see a theme. Sugar, sugar, sugar. Fat, fat, fat. And protein, protein, protein. All the things that a growing boy needs. Okay? Snickers are great in large part because they have all these things. Okay? Now, this is what a Snickers bar is, and the first thing that we know we're going to touch is the chocolate. But do you just swallow that whole? No. So what's the first thing that we do? We bite it. So, first part of our digestion happens in our mouth, where we chew. What does chewing do to our Snickers bar? It breaks it down into smaller pieces. Why? So we can swallow it, but also for something else. This is that chocolate bar. What? Did I just throw away a marker earlier? Oh, it's over here. I was wondering where my other marker. These are literally completely different colors than I had access to earlier. We've got, what is our main goal whenever we eat anything? What are we trying to accomplish? Bringing energy into our body, right? We're trying to get caloric energy into the body, which means we need to get sugar or proteins or fats into our cells so that they can turn it into ATP, right? So we are trying to absorb the monomers of proteins, fats, and sugars, and we're trying to get those to our cell. Now, how do we go from a protein down to an amino acid? Or how do we go from a big complex sugar into sugars into our blood? What do we call that type of digestion? That's chemical digestion, right? Mm-hmm. So what allows us to do chemical digestion? What do we call those components or those proteins that do chemical digestion? Online people, y'all are welcome to answer as well. Bloody hell. What do we call those things? It's not on the board. Enzyme. It's an enzyme. It's a digestive enzyme. So we need digestive enzymes. But here's a problem. Those digestive enzymes are only in water, and they're little molecular things, which means they have to get to other little molecular things. So if we just swallowed our Snickers bar whole, our enzymes only touch what? The chocolate, which means we're not going to get the protein from the peanuts. We're not going to get the fat from the peanuts. We're not going to get all that awesome sugar in that layer of caramel and nougat. Well, that's no fun. Chewing also gets us surface area. So not only does it make it where we can swallow it, but we get surface area for chemical digestion. Okay, because now our enzymes can get access to all these things. Because now we've broken it into little tiny pieces. By breaking it into little tiny pieces, now our enzymes can get to the surface of all those little tiny pieces, right? More tiny pieces means we have much more surface area for our enzymes, which means we're going to do a more efficient job of getting down to the components. Okay? So that's, of course, happening with our teeth. Now, also happening, well, I said we have enzymes. So the enzymes that we have in our mouth are in our saliva, right? So we're going to find two digestive enzymes in our saliva. We're going to find one for carbohydrates. This is called amylase. Amylase is going to help us break down carbohydrates. So if you were to put, say, a potato chip or a piece of bread on your tongue and just let it sit there for a second, it's going to start to taste just slightly sweet. That slight bit of sweetness is actually coming from glucose getting chopped off of all of the starches in that potato chip. Okay, so that's what is happening with our amylase. We also have a lipase in our saliva as well, which is going to help us start to get some stuff out of these lipids. Okay, now after we swallow, we now have a bunch of little tiny pieces going from our mouth all the way down to where? What's next? Your stomach. That's it. Now it goes down to the stomach. Now what's happening in the stomach? What do we find in the stomach? Acid. Stomach acid. So in our mouth and in our esophagus, even if I have chewed this really well, I will still have identifiable pieces of chocolate and peanut and caramel and nougat all the way down to the stomach. They will enter the stomach and be identifiable. Then in the stomach acid, they stop being. Your stomach can move, right? I can get to the picture. Your stomach has 3 layers of muscle. This oblique layer is added so that your stomach can squeeze and squeeze and squeeze on itself. It kind of slosh everything around. By doing that, it causes these things to grind against one another. They grind against one another, so they get more surface area. So more acid touches the surface, and more enzymes can touch the surface, but primarily that acid. So eventually you're going to get down to where it's just a slurry of no longer identifiable food bits, where we will have just now a mixture of lipids, carbohydrates, and proteins, all in our stomach. So that stomach acid is giving us lots and lots and lots of surface area, breaking these things down to where now we can get more and more and more surface area so that our digestive enzymes can now go to work. Now in your stomach, we're going to have a couple more enzymes. So stomach has acid, which does mechanical digestion, but it also activates pepsin. Pepsin is an amino acid. Pepsin, not an amino acid, an enzyme. Pepsin converts large proteins into small ones. It is going to help us start to break down proteins. Proteins are humongous. Some of them are 4,000 or 5,000 amino acids long. They're huge. They're also incredibly complex. They're in these big folded forms. We need amino acids. We don't need this big folded protein. So the first thing that we need to do is start to break that stuff apart. The acid in our stomach is also acting as mechanical digestion because it's basically unfolding those proteins. So that protein went in like this in a very particular folded way. Now it gets in that really low pH and it will basically unfold. Cooks it. Okay? Which means now our pepsin has more stuff to see, so it does a better job of chopping this thing into smaller proteins. But it's still not amino acids yet. That's to come. All right, so what's after our stomach? So now you've taken that Snickers bar and you've converted it into a bunch of this. The acid has now broken this down into what we call chyme. In our mouth and in our throat, so in your esophagus, we call this a bolus of food. Okay, in your stomach, it all churns together with that acid, and we're going to call this chyme. Okay, now after our stomach, where does it go? Into your small intestine, exactly. Then we're going to enter the small intestine. The small intestine has three parts. We have the duodenum, we have the jejunum, and we have the ileum. Okay? Now, this duodenum, jejunum, and ileum, each of these is going to have a slightly different function. The duodenum is going to be the first section. So in here, we're going to have a couple of things intersect with it. Namely, hold on. Namely, we will have our pancreas and our liver and gallbladder. Okay, so we have our liver dash gallbladder, and these are going to secrete what? Nope, that's the pancreas. What do we store in our gallbladder?
Bile.
Bile. Very good, it's bile. So the bile from our liver and gallbladder is here to help us emulsify. That's to say, make it mix with water, lipids. Okay, lipids do not like water. You put a stick of butter into a jar of water, you will have a stick of butter in a jar of water. They'll just stay that way. They will never mix together because the butter is a lipid, the water is water. Okay, they won't mix. So the way we make them mix, the way you clean butter off of a pan is with soap. That is an emulsifier. Our emulsifier in this case is bile. This is going to allow us to get enzymes touching the surfaces of the lipids so that we can actually start to break our lipids down. Okay? Now, we will also have a gastric lipase over here in our stomach. It'll still help us break that stuff down, but it really doesn't get access to it really until we get to the bile. Okay? Now, in addition to our bile, our pancreas is now actually going to give us the enzymes that are going to try and mix with those lipids. So our pancreas gives us anyone know what the enzymes on our pancreas are? Or digestive ones? Our pancreas, we have a lipase, which breaks down LIP. So this is going to break down lipids. So without the bile, our lipases can't get to the lipids. So this is why bile is important. This is also why people that have had their gallbladders removed have to pay very close attention to how much fat they're taking in. It is very easy for them to eat too much fat. If they eat too much fat, their stomach will be not happy with them. Okay, especially when it's their gut that's really not happy. Like if you take someone that has had their gallbladder removed and you take them to like Roadhouse and you, oh yeah, go ahead, eat some chicken fried steak and some fries.
You said I ate Texas Roadhouse, and then the next day I got my gallbladder.
Yeah, that'll do it because your gallbladder got pissed. It's like I can't keep up. Couldn't keep up anymore. Yeah, and now you especially don't want to go eat Texas Roadhouse.
Yeah.
Nope.
It's been 10 years, but
yeah, still, you can tell she has bad memories of this. The stuff that came out of her large intestine after that was probably some of the least amount of fun she's ever had. But that's because we need the bile. Without it, the fats, we can't do anything with them. So you're just left with a whole bunch of fat, which means you have a bunch of grease moving through your goose, if you know what I mean. Okay. Now, y'all haven't heard that saying? Like, no. Move through it like crap through a goose? Oh, maybe I'm just old. But that is actually, like, that was a saying, like, oh, shit, that was from the 40s. Never mind. Oh, not that I'm in my 40s, just that's how old that saying is. It's one of my favorite movies growing up was a movie called Patton. So it was about George S. Patton. Like, George C. Scott played the General Patton in that movie. And it's just awesome. Like, it's genuinely hilarious as far as movies go, or as far as war movies and stuff go. And like, he'll talk about troops moving through like the Germans like crap through a goose. It's great. That's because birds poop a lot. Anyway, we go to the pancreas, so we have these lipases that help us break down these lipids. We also are going to have trypsin, which is going to help us break down proteins. Okay, so trypsin is going to take us from small proteins to peptides. So now we can actually start to get to where we want to be, because we're going to go from a smaller protein down to some polypeptides, which means we can actually start to get access to them pretty soon. Okay. It is also going to have a pancreatic amylase. Well, amylase was also what we had in our saliva, right? And the amylase in our saliva helped us break down what? Carbohydrates. So in our pancreas, or from our pancreas, we are getting something to break down lipids, something to break down proteins, and something to break down carbohydrates. We're also getting glucagon, which turns fat into glucose, and insulin, which turns glucose in the blood into glucose in your cells. That chicken finger is kind of important, huh? Yeah. Okay, we need to take care of our pancreas. People that have pancreatitis can run into problems fairly quickly. Now, once we've done that, we now get to the jejunum. Now, once we get into the jejunum, we have small proteins that we need to break down, or polypeptides rather, that we need to break down. So what we're going to have is we're going to have a bunch of proteases to break down those proteins. So the proteins from, say, those peanuts and the proteins from that milk and that chocolate, we need to break those down further. We need to get them down to their amino acids. We're going to do that with proteases, but why don't we have a named protease? Keeping in mind that your amino acids look like this. We have a nitrogen on one side. We have a carbon, and then right here, we have what we call an R group. We have 20 amino acids, which means we have 20 different R groups. So why can we not just have one enzyme take us from polypeptides, which is to say amino acid, amino acid, amino acid, amino acid. Why do I keep drawing M's? Okay, where we have a short chain of amino acids all stuck together. Why do we need more than one protease to turn this into individual amino acids?
Yeah, well, you would think.
If we had one, it would take forever for just that one that it can break down, right? But also, they have to be specific. If we're going to break down a bond, each protease is probably only going to break one bond between two particular amino acids. We need one protease that breaks amino acid 1 and amino acid 1. We need a whole other protein to break amino acid 1 to amino acid 2. And another one that breaks amino acid 1 to amino acid 3. We have 20. That's a lot. That's a lot of different combinations of amino acids, right? And each amino acid is different, which means we need a protease for every single combination. Do y'all want to learn 2 to the 20th names of amino acids of proteases? I wouldn't either. That's a lot. Okay. So we just call them proteases to say, hey, their job is to break down proteins. Done. Good. So these are going to turn us from proteins into amino acids. So from our polypeptides actually getting us down to amino acids. Also happening in the jejunum, we have lipases, help us further break down our lipids. And we have our carbohydrases, or our amylases. Okay, but we also start to do something else, and that is finally we get to start absorbing. And we continue absorbing in the next section. Okay, now all of this stuff is in water. Those proteases dissolved in water. The lipases dissolved in water. The carbohydrates is dissolved in water. All that food is dissolved, well, in stomach acid, which is dissolved in water. That's to say, all of this requires water. Which means we have to have something else happen when we move into our large intestine. And that is namely, we need to absorb water. Once we get to the, actually, I'm going to change color here. We get to the large intestine, and we absorb water. We absorb our water, and we also absorb our electrolytes. Okay? Now, all of this is assuming, once again, though, that we've gotten rid of the lipids. In the case of someone that doesn't have their bile anymore, if they've had a bunch of fat, that means there's a bunch of fat that's going to be hitting their large intestine. That fat lines the walls of their large intestine, making it harder for them to get water out of their feces. So it's a lot of water that person's going to have to be drinking to make up for it. Okay, because you're going to lose a lot more water out of your large intestines than you ordinarily would, because a lot of water is going to leave here. And we know what that's going to be like because we've all experienced it and it's never fun. Okay, now that is our pathway for moving through stuff. We start in the mouth, we break things down, get lots of surface area. We also start to break down our carbohydrates as well as some of our lipids. And then as we move down, each component of our digestive system is going to have its own little enzymes to help it deal with particular things. Okay, so we have talked about all these parts and pieces now. Let's talk about what we're actually trying to get out of them. Namely, we are trying to get to calories. We are trying to get to our food. We are trying to get to energy from our food. We need the calories. That's the goal, right? Now, what are the 3 major components of those calories? Well, they are lipids, proteins, and carbohydrates, right? So I'm going to erase this a little bit. And I'm going to redraw some of these words. We had lipids, okay, fats, carbohydrates, aka sugars, and then we have our proteins. Right? Now, lipids, carbohydrates, proteins. Lipids we knew came from the fats in the sugar, or fats in the chocolate, the fats in the peanuts. The carbohydrates came from literally every ingredient in the Snickers bar. And then proteins, we also got a little bit of protein from the peanuts, a tiny bit from the chocolate, but quite a bit from the peanuts. Okay. Now, that's where all those came from our particular, from the Snickers bar we just ate. Now, I'm going to read off of the nutrition label. The nutrition labels on our foods are very convenient. Okay. They are going to be looking at, what am I sharing? Hold on. Let me make sure I'm sharing that screen. Okay. These are basically going to break down how many calories we're getting from each of these little divisions. And then they're going to look at different vitamins and minerals. But the first thing it will break down is fats. So in the case of our Snickers bar here, we have 6 grams of fat, and this is only if you ate 3. So serving size in this case is 3 pieces. I've had like 12 today, so don't feel bad. I wish I was exaggerating, but I'm not. We have 6 grams of lipids, okay? We've also got 17 grams of carbohydrates. You're welcome. And then we have a whopping 2 grams of protein. It's actually better than it could be. If this was a Kit Kat, there'd be 0 right there. Which is why we're doing a Snickers bar. But these are how many grams of each of these we're going to find in a serving of our Snickers bar. Now what we're going to do is we're going to calculate how many calories there are in each of these things. Now we're going to do that because lipids, or we're going to do that by looking at the components of each little thing. Now lipids, or hold on. Starting off, we're going to base all of this off of our carbohydrates first and foremost, okay? That's because our carbohydrates are actually going to form the sort of backbone for our cellular metabolism. So I'm going to rewrite this just to make things easier for me. 2 grams. Does anyone know or remember what the name of the sugar we used as our example when we talked about cellular metabolism? There was a monomer sugar that we used as our kind of example for all of our metabolic stuff. You remember what it was? We're trying to raise or lower our blood sugar levels by raising or lowering what? The levels of what? Online people, y'all are free to answer as well. What is it? Starts with a G. Glucose. Oh, shit. Glucose. Glucose is a 6-carbon ring. It's glucose, okay? Now, whenever your body takes in glucose, which like I said is a 6-carbon ring, so 6 carbons, okay? The first thing that we're going to do is we're going to chop it into 2 3-carbon chains. 1, 2, wait. 1, 2, 3. We call this process glycolysis because we are breaking glucose. Glycolysis. We get a couple ATP out of the deal. Because remember, the whole goal out of all of this stuff is to get ATP because ATP is our cellular energy. Okay? So we go through glycolysis and we generate this 3-carbon thing. But then we ship it where? Where does that 3-carbon thing go? It enters our mitochondria, right? That thing with all the folds on the inside. Okay, so it enters our mitochondria, but it enters as a 2-carbon chain. So carbon connected to a carbon. And then this enters what we call the citric acid cycle. Citric acid cycle, which is a cyclical set of chemical reactions that are going to do a couple things. Namely, they're going to give us some ATP, but they're also going to load a whole bunch of energy trucks. So high energy carriers. Okay, these are NADH2 and FADH. So this is all from like chapter 3. Okay, so we're going to load a bunch of these energy carriers. These energy carriers then move over into our next step, which is called the electron transport chain. Electron transport chain, which turns those high energy carriers into ATP. If we can do all this, a single glucose gets 2 ATP here, another 2 ATP here. Actually, I hope, yeah, 2 ATP here, 2 ATP here. But here, it makes 34. Which really tells us making ATP relies on this step. Okay? Going through the citric acid cycle, loading these energy carriers is where we're going to get the vast majority of our ATP. Okay? So here's the fun thing. Anyone remember what a lipid looks like? So, carbohydrates. Back to that. A carbohydrate, so based off of our little nutrition label up there, a carbohydrate is going to give us 4 calories, or 4 kilocalories per gram. We had 17 grams. So how many calories are we going to get from our carbohydrates? Well, each gram of carbohydrate will get us 4 kilocalories of energy. So if I want to figure out how many calories I have from the carbohydrates in my Snickers bar, I just need to multiply my 17 by my 4, because I have 17 grams. 4 times 17 is what? 468. So I have 68 calories coming from my carbohydrates. Proteins will enter here. So these proteins, wish I had done this in this color. I'd commit that. Never red. Proteins, remember, are a carbon touching a carbon with an R and then an N, right? So what we need over here is carbon touching carbon, right? We've got one. Although now we have a problem. Those carbons have a nitrogen on them. So what do we need to do? We need to get rid of that nitrogen. So we're going to chop this nitrogen off. And this nitrogen is going to be found in a form called urea. Anyone want to guess where you're going to find urea? In your urine. Man, that is conveniently named. Almost like it's that way on purpose. Okay, so the nitrogenous waste from us doing protein metabolism, that's to say, turning protein into caloric energy in our cells, is going to make urea, which is going to be the main nitrogen-containing component of our urine. You break down proteins for food or for energy, you will produce urea, and thus you'll have to produce urine. Easy peasy. Okay, but however, that also gives us a 2-carbon chain, which can conveniently, guess what? Enter our citric acid cycle. Well, the whole goal here is to, wait, hold on, it's to make ATP. We have just turned a protein not into another protein, so like incorporating it into muscles, like into the muscle fibers, or incorporating those amino acids into our own cells to do other things, which you will do with some of them, like 10% of them. The other 90% of the protein that you take in as your diet gets turned into energy at a rate of 4 calories per gram. So if we have 2 grams of protein in our peanuts and a tiny bit in the chocolate, so we have 2 grams of protein in our Snickers, we're only going to have 8 calories of protein, or from our protein. It's not bad. Okay, but 8. Okay. However, this R group can do something weird too. Part of that 4 is because some of these R groups, not all, just some, can also find their way into our citric acid cycle. If we can convert this R group into one of these intermediates, because this is like 10 steps or something like that, if we can convert that R group into one of these intermediates, we can get energy out of the R group too. So there's actually going to be some variance in how many ATP we can generate from each amino acid based off of the R group, because we can utilize some R groups and some we can't. Does that make sense? But on average, it works out to about 4 calories per gram. Okay, so we've got 8 calories from our Snickers. Here's the fun bit. 6 plus 8 is what? 76? The total calories for our Snickers bar are 130. 130 minus 76 is going to be 54. How many grams per calorie is that for lipids? Anyone good at math? 9 times 6. This is 9 calories per gram. 9. That's a lot. Why is this over double the caloric density of carbohydrate? We have almost as many calories from our 6 grams of fat as we did from 17 grams of carbohydrates. Why is it so much more calorically dense? What do lipids look like? What is a lipid? They are, very simply, a carbon connected to a carbon, to carbon, to carbon, 50 or 60 times. That's it. They are a chain of nothing but hydrocarbons. So this carbon has a hydrogen here, a hydrogen here, and a hydrogen here. This one has a hydrogen here, and a hydrogen here, hydrogen here, hydrogen here. So it's basically just carbon, 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 carbon. They're hydrocarbons. They're made out of nothing but carbon and hydrogen in a long chain. Well, we need carbon, carbon to enter our citric acid cycle and make a bunch of ATP, right? So we can do that here. We can do that here, 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 and here. From this one lipid, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 full turns of the citric acid cycle. Which means I can take that 9 turns, and each one of those is going to turn into roughly 17 ATP. That is why lipids are so efficient, because they are basically just raw ingredients for the citric acid cycle. Every 2 carbons you can chop off, you get a full spin of the citric acid cycle, which means you get 17 ATP out of the deal. 2 more carbons, 17 more ATP. 2 more carbons, 17 more ATP. 2 more carbons, 17 more ATP. Over and over and over and over and over again. And like I said, they're really dense in the chain. But here's the fun bit with lipids too. And that's that things like this line up really, really tightly together. If you take just something like this little chain right here, and just kind of melt a bunch of it from, say, a pig or something like that, and then you let it cool, you know what it turns into? Just a brick of fat. Lard is just that in a jar at room temp. That's it. Just a bunch of carbons. The stuff that's in the gas tank of your car, that. So some of them are in circles. Yeah. Okay. So this stuff is incredibly energetically efficient. It's very energetically dense. Why? Because you can pack it into really tight areas. They pack really tightly together. Fat likes to stick to fat. Okay. But that's just because things that are hydrophobic tend to stick together, and they're going to stick together because they're hydrophobic. So they're just going to stick and stick and stick and stick and stick. Okay. So we can make them incredibly dense. So we get 9 kilocalories per gram of our lipids. So this process of looking at like, okay, we know that lipids are 9 grams or 9 calories per gram, proteins are 4, carbohydrates are 4. What I want y'all to do as kind of an extra credit assignment is basically going to be to look up kind of one of your favorite snacks, one of the favorite things you have to eat, and then give me a kind of real quick like breakdown of its components, and then tell me how many calories there are for each component. So if I were to write down Snickers bars, in this case, a serving of these mini Snickers, it would be 54 calories from fat, 68 calories from carbohydrates, and 8 calories from proteins. And then maybe tell me why you like them. Okay. And that's in one of the little discussion boards in Blackboard. Okay. That'll be a couple extra credit points for you. This will also kind of let me get to know y'all a little bit. Just because I can judge people based off their food. Now, I'm not saying that you need like, oh no, I like all these healthy snacks. Bullshit. It's like, maybe it's true, but don't tell me that, oh no, there's 7 calories per 6 ounces, 6-ounce serving of my like carrot snack, which I know good and darn well that that's not the only thing you're snacking on, but it's fine. Like, okay, like you can be like, it's a healthy, balanced diet, right? Now, oh snap, what did I just break? Okay. It just broke on this screen on this one. All right. Now, there are lots of other things on here. So each one of these little tabs that you'll find in Blackboard is also going to go into a little bit of depth about things like saturated fat, or why it's good or why it's bad, cholesterol. Why do we need fat for our cells? Anyone know? Why do we, or do we use fat for anything in our cells? What? No, I don't mean like for energy wise. I like not energy related. Do we use fats as structures in our cells? The answer is yes. So what do we use the fats for as structures in our cells? What's on the outside of your cell? What forms the boundary of your cell? Not a wall, it's a membrane. Our cell membranes are made up of lipids. All of the membranes and all of our membrane-bound organelles are made up of lipids. So we need lipids as raw materials to make cells. Okay? We can't make membrane without lipids. Proteins, well, we use amino acids to make protein. So some number of those proteins that we take in our food will be used to make additional proteins in our cells, whether it's keratin protein in our skin cells, which we make a boatload of because we're constantly replacing all of our cells all the time in our skin. We have to make a boatload of keratin, which means you have to take in some amount of protein every single day just to make sure that you can continue making all of your skin cells. Wait a minute, you've probably heard this before in an ad somewhere, right? Whether it's a YouTube ad or a commercial where they're talking about taking collagen peptides. They're going to mix some collagen into a jar or something like that. By the way, collagen is also the shit that they put in glue. Just because they're telling you it's collagen, yes, we use collagen in all of our cell types everywhere. Okay, collagen is a very, very important protein that we use a bunch of. And one of the best places to go get a whole bunch of it is in places like the feet of cows and horses, because that's the structure that gives their hooves their structure. So don't trust the collagen stuff as being like, oh, no, this is healthy. I mean, it's fine. You can eat cow hoof. That's totally cool. But don't think that it's ever going to be an appetizing thing. Okay. But they're mixing all of that collagen and stuff into their water. Guess what they're really mixing in? Protein. That's all it is protein. Okay. It is a certain type of protein, but it's still just proteins. We're adding raw amino acids, like we're putting amino acids into the stuff. Okay. There's very little difference in my eyes or in my mind of someone like, oh, here's some like collagen supplements to your drink, as it's like you're basically taking a whey protein powder shake. Like, it's for functional purposes, it's the same thing. Both of them will make your hair, skin, and nails look great. And if that's what you're looking for, awesome. But guess what? If you're not getting enough protein and stuff in your diet, your hair, skin, and nails probably aren't going to look good. Why? Because they're made up of protein. Make sense? Now, there's also some little blurbs in here about fiber and various types of carbohydrates and stuff like that. Fiber is very important as a part of our diet, but fiber doesn't count towards this calorie bit. That's because we don't break down fiber in the same way. Fiber is really, really tough. Fiber is made up of the cellulose, which is in the cell walls of plants. And those glucoses that make up that fiber are in a giant chain that could literally be 200,000 units long. Whenever you go to digest it, you get the ones off the ends. That's it. You get the ones off the ends, which means if you're going to get any sort of nutrients or any sort of energy out of something like grass, you have to chew it a lot to try and break down some of those proteins on your own. You have to do as much mechanical digestion as you possibly can to try and get any nutrients out of it. And even then, even if you do this really, really hard, like say you chewed a whole bunch of grass, you swallowed it, got it down into your stomach, then you throw it back up into your mouth, chew it some more, and then swallow it again. And so it passes through your bowels. It will pass through your bowels. You'll pass it. You'll defecate, and there will still be identifiable species of grass in that feces. That's what cows do, not humans. But if you've ever looked at a cow patty, you can literally identify which species of grass they are eating, because that's how identifiable it still is on the other end, because that is how undigestible cellulose is. Like with corn, those little fiber bits on the outsides of those corns, yep, it just stays there. That's also why a bunch of people in Spain were eating corn as their primary sort of grain for a few years, and a whole bunch of people died because it turns out that they were like under-nutritioning themselves a lot because they weren't getting any of the calories from it. Because they weren't able to break it down efficiently at all because of that little pericarp on the outsides of the seeds. There is a process for getting rid of it, though. Have you ever had hominy? Hominy is basically you take the corn kernels and then you run them through a mixture of essentially lye. And it basically just degrades that outside bit for you. It also makes them swell up a little bit because they take on a bunch of water. But then the hominy at the other end still tastes like corn, just kind of a sharp version of corn. But now you can get all the nutrients from it. So when that process of like putting it through the lye and kind of getting rid of the outside is called nixtamalization. Nixtamalized corn or hominy. But that's how we get nutrients from it. If you take that hominy though and you break it into a bunch of little pieces and put it flat and then you throw it on a griddle, you know what you call that? A tortilla. I'm actually not even joking. That's literally how they make tortillas. You take corn, you nixtamalize it. So you basically like soak it in some stuff and you turn that into the hominy. And then you basically take that hominy and then you make it into a paste. Like you grind it all up and force it together and you call that masa. And then that's what you use to make tortillas. Like that's literally not a joke. That is just how you eat those things. But that's how you make a tortilla. But also that's how you go from something as inedible as corn and turn it into something as awesome as a tortilla. God, I love tortillas. Make some salsa, maybe some queso. Oh man, I love food. I'm also hungry already. Again, damn it. I wasn't even going to eat lunch today. Then I did this whole spiel in the first class. Like, well, I guess I have to go eat lunch now. All right, so there's some stuff in here about all these. Now, but it's not just about getting calories out of our food. We also need to get a bunch of vitamins and minerals. There are certain kind of what we call micronutrients that we need out of our food. There are lots of different kinds of these. It could be a mineral, which is to say we have some inorganic thing, which might be something as simple as calcium that we need in our bones. So we're going to take that calcium from something like, say, spinach or kale, and then we will turn it into calcium phosphate salts that we will use to make our bones nice and hard. Or it could be something like a vitamin, which is going to be a small little set of proteins, or usually a single amino acid, that we would call a vital amine, or thus vitamin. Okay. These vitamins are basically going to be small things that are going to contain some nitrogens that are going to help different cells do different things. So there's a nice little table here talking about each one, or talking about some of our vitamins, and then exactly what those vitamins are helping us do, or at least kind of a broad strokes view of what different vitamins are helping us do, as well as where you can find pretty good amounts of those. So that can make this at least a fairly fun thing to look through. Like, something I find fun, like with a table like this, is like, okay, I really like to eat, say, nuts. Okay. Like, I'm a sucker for pistachios. Like, if you give me, especially like when they're already shelled, so you don't have to deal with all that BS, like pistachios are amazing. So then it's like, oh, hey, look, nuts. Like, that means if I eat a fair bit of nuts, I'm going to get some vitamins. I'm also going to get some, keep looking, keep looking. Where do we see nuts again? Where do we see nuts again? Oh, damn it, there's not very many. Oh, here's one, thiamine. I'm getting thiamine as well. But then it's also going to make you realize, oh shit, I need to eat a whole bunch of different stuff if I'm going to get all of these vitamins and things like that that we need. That is where we get to having that balanced diet. Okay. There's nothing wrong with eating a cheeseburger every now and then. There's not. Or Oreos or whatever that may be. As long as you're keeping things within proportions most of the time, it's going to be okay. But over the course of a week, you need to eat something where you're going to get some amount of this. You need to eat some stuff that's going to give you this. You need to eat some stuff that's going to give you this, which means over the course of a few days, you need to eat a pretty good mixture of a bunch of different stuff. That's really what it boils down to, is the more varied your diet can be, the better off you're going to be at getting all of these vitamins, all the minerals that you need, as well as making all of the bacteria in your gut happy. And that is really what it all comes down to. Okay. So look through these things, look at the various vitamins and stuff like that. I'm not going to point out any more specific ones. Y'all know how to read. But there are some fun ones in here. And there's lots of different ways to read through this in ways that you can kind of get something for yourself out. Okay. Everybody good? All right. So we have talked about the different parts and pieces of our digestive system. We've talked about how we're going to get different enzymes to help us deal with lipids. So remember, our enzymes to help us break down lipids are lipases, right? Lipases. And we get those lipases in our saliva, in our pancreas, in our stomach, and in our small intestine. Proteins. Well, these are proteases that we get in our small intestine. We have pepsin in our stomach. And we have trypsin in our pancreas. Carbohydrates, we have amylases. And we have those where? Where do we have amylases? One was in our and your saliva. Very good. Both of y'all said it kind of the same time, which is awesome. Our saliva, and then we also have another one from our pancreas. Make sense? So we have lots of different ways that we can look at this. We have lots of different ways that we can think about this. So that's kind of the main thing that I want y'all doing, like with this whole Snickers demonstration or idea, but also like with the snack discussion board as well. Just, I want you to think about some of this. Like, hey, all right, say this snack that you're going to talk about, or your meal that you're going to talk about, is fried chicken. Well, that's going to be carbohydrates in the flour. It's going to be fat in the flour, and well, probably not in the chicken, because well, it's probably chicken breast. But some of the fat will have gone from the oil into the chicken. And then there's also going to be a bunch of protein from those like chicken breast fibers. And then tell me kind of where some of those things or like you can think about where some of those things are broken down. Like most of the protein is going to get, you're going to go from big proteins to little proteins in the stomach. You're going to go from little proteins to amino acids in the small intestine. You're going to go from starches on the outside of the chicken. That's going to start breaking down in the mouth, which is part of why they're slightly sweet, which is part of why we enjoy them and all that kind of fun stuff. So just kind of think about those things while you're eating whatever it is that you're eating. Very good. And we're done. We do not have class next week. You have an exam that is due on Monday or Tuesday. Make sure you do that. Take your time. Now that we don't have class, now you have more than sufficient time to have a chance to do that. You shouldn't feel stressed or anything like that about it. Get that done. That'll be your module 3 exam. Hope y'all have a great Thanksgiving. I hope you think about some of this stuff as you're eating pounds and pounds and pounds of turkey. Maybe talk about this while you're eating the turkey, because goodness knows there are much scarier topics to be talked about at a Thanksgiving dinner table. Mine just turned into giant like complaining fests from people, which is great.